In this video, we are going to start Unit 7, which is on oscillations, waves, and sound, and today's particular lesson is on oscillatory motion. So an oscillation is defined as when an object moves back and forth around a position of equilibrium. It can only happen when there is some sort of restoring force that, causes the object to go back to equilibrium. And then oscillatory motion is back and forth motion across the same path. There are lots of examples of oscillatory motion in everyday life. The most simple example is what I have in the background here. It's a pendulum. So a pendulum moves back and forth over the same path. And in this video here, and I've slowed it down so we can see it a little bit more clearly, it's a mass on a spring, so you can see that this cart is going back and forth across the same path. And let's think of some other examples. Well, our heart beats, so that's an example of oscillatory motion. And if you play a stringed instrument, the string moves back and forth, so that's oscillatory motion. So there's just lots of examples in everyday life. A restoring force is a force that always pushes or pulls the object to the equilibrium position. And remember the equilibrium position? This is going to be when the net force on the object is 0. Here's a bit more vocab related to oscillatory motion. So the period is the time for one complete cycle of an oscillation. So a cycle is when the object returns to its original position. So if we have a pendulum, and the pendulum goes over here, and then back over here, so forward and then back, that is a cycle. And the units are in seconds. Frequency is called the number of oscillations, or is known as the number of oscillations per unit time. The units are hertz, and a hertz literally means how many cycles per second. Last piece of vocab here. The amplitude is the maximum displacement of an oscillation from the equilibrium, and that should say position. From the equilibrium position. So you can see in this diagram here, so this right here is the equilibrium position. So this distance right here is the amplitude. And the amplitude can be a stretch or a compress for a spring. So it can be negative or positive, because technically this would be the positive direction, and then back that way would be the negative direction. So again, here is where the equilibrium position is in this diagram, and then this distance is the amplitude. Now for this pendulum, I would say right in the middle there is the equilibrium position. And then usually for a pendulum, let me redraw that real quick, it's by angle. So this angle here is the maximum displacement from equilibrium. That's the amplitude of the pendulum. Now, simple harmonic motion is a specific type of oscillation in which the restoring force is proportional to the displacement from equilibrium. So all simple harmonic motion is oscillatory motion, but not all oscillatory motion is simple harmonic motion. And simple harmonic motion is abbreviated to SHM, so we can abbreviate that if we like. So a mass on a spring and a pendulum are two examples of SHM. Now, it's only simple harmonic motion if the amplitude is low. So if the spring is stretched too much, or if the pendulum is lifted up too high, then it's probably not going to be simple harmonic motion because the amplitude is too high. So if the amplitude is too high, then the force is no longer proportional to the displacement. And since that's the definition of simple harmonic motion, it would no longer be simple harmonic motion. When the force is proportional to displacement, the patterns are a lot easier to predict, therefore it's easier to study. The last thing we're going to do in today's video is we're going to learn how to calculate the period. So everything for oscillations and simple harmonic motions is included for you on your equation sheet on the AP Physics 1 equation sheet in these three equations. So this equation here is for the period, and that's just period in general. It could be period for a mass on a spring or a pendulum. So what this says is that the period is equal to 2 pi over omega, where omega is something called the angular frequency. We're going to get to more about that in another video. What I really want you to look at here is that the period is equal to the inverse of the frequency. So period and frequency are inverses. So you could also rewrite it like this. F, the frequency, is equal to 1 over t. So the formula for a mass on a spring is symbolized by T sub s, so the S stands for spring. And that says that the period is equal to 2 pi times the square root of m over k, where m is the mass of the object and k is the spring constant. And notice that this formula does not depend on how far you pull the object from equilibrium. So think about why that might be. And for a simple pendulum, the period is equal to 2 pi times the square root of L over G, where L is the length of the string and G is the acceleration due to gravity, which on Earth is 9.8, as we should know by now. And it's symbolized by a lowercase cursive L on the formula sheet. So notice that for a simple pendulum, it does not matter, the mass of the pendulum does not matter, and it also doesn't matter how far you pull the mass from its equilibrium position. So let's do an example problem real quick. So you make a simple pendulum by hanging a small 60-gram marble from a light thread of negligible mass. The thread is 0.4 meters long. We want to find the period when the marble is pulled a small angle to one side and released. And we also want to find the frequency of oscillation. So we just want to use this formula here. So the period is equal to 2 pi times the square root of L over G. That's going to equal 2 pi times the square root of 0.4 over 9.8. Notice that we did not need the mass of the marble because the mass of the marble does not affect the period of oscillation. So if you plug all of that into your calculator, you should get that the period is equal to 1.27 seconds. So that is our answer to part A. And for part B, well, remember that the frequency and the period are inverses. So if we just take the inverse of 1.27, we get 0.79. And what are the units there? Well, the units for frequency are hertz, which we can abbreviate as Hz. Now I do want to show you guys a brief calculator trick for getting the inverse. It'll make your lives for this unit a bit easier. So I'm just going to show you how I would plug in the problem. So I would first just do 0.4 I rounded up to 1.27 seconds. And then there's this button right here. It says x to the negative 1. So that's how you can just really quickly get an inverse of your previous answer. And that gives us the frequency. So I hope you found this little calculator trick useful and that you learned a bit more about oscillations and simple harmonic motion.